We are now looking at the master questions in our first lesson in the chapter regarding integration. The first question is this one. It is from October-November 2009 paper, and it's question 1. And it says the equation of a curve is such that dy by dx equals 3 over square root of x minus x. Given that the curve passes through the point 4, 6, find the equation of the curve. I have to say that they were very nice to put this question right at the beginning, just for the students to gain momentum and trust, because this is a basic question, as you probably already noticed. You just have to integrate that function, which is not hard at all. Use the point to get the arbitrary constant, and basically you have 4 free points, right? So here you have it. You just write this in the index form, making it much easier to integrate. Integrate to each one individually, all right? And this is what you get, the general expression, the general solution. Then use the 0.46, substituting 4 on x and 6 on y to get the value of c. And then rewrite this with 2 instead of c. And that's answered already. Next one is also from October, November, but now 2007. And the question is this one, question 9, a total of 9 points. Let's see what it says. A curve is such that dy by dx equals 4 minus x, and the point P, 2, 9, lies on the curve. The normal to the curve at P meets the curve again at Q. And you have to find first the equation of the curve. So this is just the same as the question before. The equation of the normal to the curve at point P, and then the coordinates of point Q. Okay. So let's look at the expression. We just have to integrate this to get the expression for y. Very simple to integrate. Here it is, the general solution. Use point P 9 to get the value of c. Substitute c by 3, and you get the final equation of the line. Here written in terms without the denominator over there. Okay? Then what is the gradient? They want the gradient of the normal to the curve. How'd you get that? First, you need to get the gradient of the tangent to the curve. And the gradient of the tangent to a curve is given by this expression over here. Don't forget, the dy by dx gives you the expression of the tangents to the curve y at any point with x coordinate x, okay? In this case, is 2, right? So substitute x by 2, and here you have the gradient of the tangent. Now that you know the gradient of the tangent, you can get the gradient of the normal by doing minus 1 over whatever that is, so 2. You are almost done with the equation of the normal. You just need to get the value of the y-intercept, c over here. For that, you need to know a point that belongs to the curve, which you do. That is the point that is tangent to begin with, so 0.29. Substitute 9 on y, x, 2 on x, and you get the value of c, which is 10. And here is the equation of the normal, again written underneath after the removal of the denominator. Then it says that this curve crosses the line, which is a parabola, again at point Q, and you need to get the coordinates of that point Q. So again, it's just a question that could be on the first chapter that we've studied. So you'll do simultaneous equations. In this case, I think it would be simpler to get the coordinates of x and y. And by solving this, I use elimination, and I get these two values. Unsurprisingly, one of the coordinates is the coordinate of the point P, which we already knew is a point of intersection of the normal with the parabola. And the other one, here this one, 7, 6.5, is the coordinates of the point that we want, point Q. Okay? Finally, we have this question, a winter 2014 paper, question paper 13. And the question is this one over here, 8. with 8 points. A curve y equals f of x has a stationary point at 3, 7 and is such that the double derivative of this, the second derivative of this, equals 36x to the power minus 3. State with a reason whether the stationary point is a maximum or a minimum. 1 point. 1 point suggests that the answer is somewhat obvious, and it is. You already have here the expression for the second derivative, and you know that after substituting the x on the second derivative by a particular value, you will know if that point is a maximum or a minimum, assuming that you already know beforehand that the coordinate that we are talking about is a stationary point to begin with, which you do because the question tells you, right? So you know that this is a stationary point. So if you substitute on the second derivative x by 3 and looking to the sign that you'll get, you'll figure out if it is a maximum or a minimum. So that's what I did. I got this value. You don't even need to bother to calculate it. You just need to show that it is, in this case, positive. So if it is positive, this is a minimum. Okay, so you get that point. Then you want to know the value of the derivative and the value of the function itself. Okay, you are given an expression for the second derivative. How can you get an expression for the first derivative? Well, integrate this. You integrate this function and you get this one again, the general solution with the arbitrary constant. And now what point do you use to get the value of the arbitrary constant? It's not this one, all right? This is a point that belongs to the line, okay? Not to the expression of the gradients, which is this one. What do you use instead? You use the fact that this point is a stationary point. What does this mean? This means that if you substitute x by 3 on the expression that you have here, you don't have 7. You have what? You have 0. Okay? Don't forget what this is. This is an expression for all gradients. Okay? So if you know that this point is a stationary point, what does this mean? This means that the outcome that you have of this expression after substituting x by 3 is a gradient of 0. Stationary point means points where the gradients are 0. Okay, so I have here 0 on the dy by dx. I have 3 on the x, and I have, after solving, 2 as the value of the arbitrary constant. So I rewrite the expression for the first derivative as minus 18 over x squared plus 2. Okay, so I already know over here the actual expression to all possible gradients already removed of the arbitrary constant, which is 2. For the function itself, we just need to integrate this again. That's what I did over here. You will have this expression again with a second arbitrary constant, but for this one, we will already use the point that we know that belongs to the original line. So in this case, 7 goes to the y, 3 to the x. We solve for the arbitrary constant. It is minus 5. And we finally rewrite the function that we got here, substituting c by minus 5. And this is what we get.